Okay, so this class is a really exciting class. I can see I do have my website. The URL is electronics.com. It's not exactly electronics, but electronics, YI electronics. So I recommend people probably sitting over there because it's not, we don't have full projectors. I decided to use Canvas as well. In the past, I let my students post their reports to my website. It's gonna be a lot of work for me to give you every one of you an account to my website. So let's do Canvas, and I think it's working really well. You can see I already posted several assignments. We have homework 1, quiz 2. I don't count attendance, but we do have, it's not daily, but probably twice a week for quizzes. So these are the links to all the courses and labs. So it's a 4 credit class. You can see all these are the schedule for this class. Oh, I haven't updated yet. Have I? Okay, so it's a pretty old. I haven't updated yet, but we can definitely see the all the assignments over here. But let's take a look at the syllabus really quick. See the look at the requirements. Don't take too much time from you. So much things to cover today. So you can see I have the links to the course webpage, which is electronics.com, the lab webpage, and my homepage. Okay, I think one or two. One required textbook, Dr. Baker's textbook, which is who is my advisor in my PhD, and the other one is pretty classic VLSI class in the industry. So a lot of people are using that one, but it doesn't have too much simulation files. That's why I prefer my PhD advisor's textbook a little bit more. And we have homework quizzes, lab reports taking 70% of the grade and 10% for midterm exam, just one midterm, not two, and one final exam taking 10% and 10% for project as well. Any question on this? Grading skills? No? Okay. So the links to the syllabus or the schedule you can find from this webpage, and the lab schedule you can find from here. You can see I made several changes. I removed lab 1 in the past. I let students to do circuit simulations with LT Spice for the first lab, but I removed it since I think it's really simple. How many of you are not familiar with LT Spice? Have you done LT Spice in the past? It's circuit 1, right? Okay. A labs, that's what we used to do, but I'm adding another 3 or 4 labs. So it's a heavy load alert. Okay. The reason we want to do that is, we most recently we got a Cadence server set up. So in the past, we do have a Cadence server already. It's something really exciting. Let's explore tutorials. And you can see the VLSI design tutorials. You have electric VLSI, which are 5 basic tutorials. None of them are labs for this semester. So these are just the basic tutorials. You just have to go through them and be able to know how to run electrical VLSI on a computer. Okay, and there's another industry standard tool called Cadence design software. It's more complicated, but the thing is, if you directly work on Cadence, probably 80% of the time you are going to focus on the tools, debugging the tools instead of the design rules and all the knowledge we are going to cover this semester. So it's taking a lot of time to learn, the tool itself, which is not ideal. However, I still think that's important, even though it's the introduction to VLSI. But I think after we studied all these electric VLSI open source stuff, because it's easier, you only need to focus on how to lay out the inverter, how to lay out the AND gate, and put them together, make an ALU. Eventually, you can see the 8th lab, which used to the last lab in the past semesters. So you can tell this semester will be way more rigorous compared to the past. So you can see we'll finish everything, all the 8 labs, pretty much at the 8th or 9th week. I think probably the 9th week because this one takes 2 weeks of lab efforts. Why? Because just so many stuff to be laid out over there. So you can see these are mask design and layouts for a 8-bit AND gate, I think. Okay, it's AND gate. And this is a very simple ALU, part of the CPU. And eventually it looks like this. And if you zoom in, you'll see these are single gates or single gate. And you put them together to form an 8-bit gate array. And eventually form an ALU. It takes a lot of time. So I'm gonna let you guys work on this for 2 weeks. Okay, and right after this, I'm gonna add the Cadence Virtuoso stuff into the semester. So I think you know Ian Van Horn. He worked with 2 industry guys. One from WDC, which is a company focused on Verilog design. Most of you will be in the embedded class as well. Learn how to do Verilog and digital design, right? And so it's called front-end design because people focus on the code itself to write the code for digital hardware design. And there will be another group of people focused on back-end design, which is mainly just layout. Could be the Cadence tools. You just saw the layout figures, right? And also Innovus timing design as well. So these 2 parts will form a big team for integrated circuit design in the industry. It's really exciting industry that you guys wanna probably hopefully you guys can get into. The reason for that is for this college or other schools, for example, Colorado School of Mines or Civil Boulder, all the other engineering schools, the students in electrical engineering, most of them, if they're doing well, are mostly going to the defense sectors. For example, the national labs or some of the contractors are giving people $90,000 as a starting salary. Sometimes after 2 years, they're receiving 100K, and that's considered as a good job already, right? I think if you guys can get into this kind of industry, it's good. But after the inflation, it's not good anymore, to me, I think. And you can see the people graduated from here, I think how many of them? 70% of the students graduate from here went to this kind of industry, just defense industry, okay? So they are very good at hands-on skills, making PCBs and integrated circuit design or coding. Doesn't matter which skills, but they were pretty competitive. And the only chance that I can receive something around 200K is getting to the integrated circuit design industry. It's very interesting. So either do FPGA, very deep digital design, or just purely integrated circuit design. The bar is higher, but it's more rewarding. So that's why I'm getting pretty excited about this. I'm also hoping that after getting all these industry design tools like Cadence and Innovus into the server, and we were able to get all the workflow from scratch, from nothing to a chip, and eventually not everyone I know, but most of you probably can get a job in things like Apple, Samsung, Qualcomm, places like this. We'll see if Ian can get into one of the jobs in the big players. So you guys can just follow that path. Okay. So he already established the entire workflow from just RTL, from Verilog to a chip. And we submit that chip to TSMC. That was probably 3 weeks ago. We'll receive it in February. And eventually put on the wire bonding machine and do the wire bonding and test it. So it's eventually just a microcontroller that we can program. Eventually in the future, we'll design our own chips from RTL, just not from nothing, right? From scratch. And if we're gonna get a chip with all the CPUs and memories on it, and we'll program it and develop probably 10 tutorials and put it into microcontroller class. So students will learn how to do VLSI design and microcontroller programming with assembly and C using our own chips instead of Arduinos. Is that exciting? It's the only thing keeps me awake. Getting depressed recently, have to work out in the morning to be excited. And whenever I think about this, getting excited again. All right. Don't want to take too much time from you guys. Let's see what we have to do, okay? Go back to here. Not this one, sorry. Yeah, directly probably read on the papers. So fundamental circuit series first. Why? Because the first lab, take a look at this. The first lab ever will be a ADC to DAC, but these are not physical ADC and DACs. What is an ADC? It's an analog to digital converter. You'll be more familiar with the terminology. Don't get scared. I'm sorry for that. Later in the semester, you will be familiar with all these terms. So ADC is analog to digital converter. You have been using some of the Arduino kits, right? So all the A0 to A5 ports are A means analog. So these are taking analog signals and digitizing them and putting all the digital data into the memory. So ADCs are the front end digitizers that digitize all the analog signals. And so you can imagine that the ADC's output will be digital signals. Digital signal will be multiple bits. You can see this one has 10 bits. And being connected to another 10 bits for the DAC. So DAC is digital to analog converter. So the digital signal is being received by the DAC. Also, sometimes we call it a DAC. So a DAC receives the digital signal and convert it to an analog signal. You're thinking why we are doing this. It makes no sense. You have analog signal, digitize it, and then convert it back. Just trying to verify it works. It's the very first lab, and you guys are not designing any of these, but just directly load it into electrical VLSI, which is the software you are seeing here. Just load it in there and run the simulation. So the goal is to practice SPICE code, okay? You see, it's being digitized. It's not directly, because it's not ideal ADC, definitely you are getting errors. So the sine wave here is the analog input, and this one is the DAC's output. Getting stairs because it's not perfect. It's only 10 bits. If you are using like 20 bits, so probably you have to zoom in to see the stairs. Okay. And using a resistor, it's called R2R ladder. Getting 1R, 2R ladder to form a DAC or DAC. It's a really simple DAC. And so for today, we're going to cover the theory behind it. How do we calculate the voltage output for this DAC? So understand what's going on here, okay? All right, that's everything for lab 1, and that's why we have to cover the fundamental theory behind the scene of this guy, okay? So the video, the lecture is being recorded. I'm going to post it to my website after this. So the URL is lec1.com. You can click. It's actually the course web page is on the home page. You can directly click that link to get into the videos and lecture and also the notes. So first of all, we have to just a really quick review. All right, it probably will bore some of you guys. 7 is equivalent, really quick, only in 2-3 minutes. R1, R2, R3. Why do we have to do 7ing? Because it's part of the DAC. How do we convert it to its 7 is equivalent circuit? So basically you are looking for VTH and RTH, right? How? Where's VTH? Here or here? Do they have the same voltage? Why? Is there any current going through here? No. So voltage is the same. So VTH. So no current, no voltage drop. So VTH is over here. So VTH equals current divider series V in times R2 over R1 plus R2. What is RTH? Looking backwards, it's R3 plus R1 in parallel with R2. Any question on this? Feel free to ask. We're not spending, 1 more second on this one. It's super basic. It's recorded. If you're not getting this, definitely watch the video and, look at the notes. Okay? R1, R2. So what is V out? Because they have the same current, right? So V in divided by R1 plus R2, that's the current you're getting here, times R2 will be V out. Okay? Or you can say V out equals R2 over R1 plus R2 times V in. Voltage divider, very simple. Not spending one more second on this, okay? So what if I have a circuit like this? This is still V out. Can I say that V out equals R2 over R1 plus R2 times V in? Is this correct or not? If not, why? I want to hear that answer. Yes or no? Why?
Because there's current flowing.
Mm-hmm. Because they don't have the same current. This guy has the same current, so you can do it this way. This one, they got current split into two branches. So this is wrong, right? Okay, cool. Spice. What that spice stands for? Something in the kitchen? Yeah. Like a simulation program for integrated circuit emphasis. It's gonna be on the quiz, right? Kidding. Why? Because my graduate school teacher put it on the quiz. R2, R3, let's say it's a 1K resistor, 1K, 1K. How to write the spice code for this guy? Starting from where? Starting from labeling the nodes. Can I label this as 1, 2? What about here? 3? No. In spice, if it's a ground, you want to label as 0. Keep in mind, it's ground. So it's going to be VI. It's from node 1 to 0 because the voltage drop is from 1 to 0. The drop is from 1 to 0. That's why it's a VI. Doesn't have to be VI, can be V anything, but has to start with V in spice. Same for resistors. It has to be started with R. Capacitors has to start with C. You can name it whatever, like V Durango, V anything. It's still a voltage being treated as a voltage. So VI is 1, 0, the two nodes to show the connections, and it's 5 volts, right? And R1 is from 1 to 2, and that's 1K. And R2 is from 2 to 0, and that's 1K. And R3 is from 2 to 0, and it's 1K as well. And that's the circuit. That's a spice code for the circuit. And you don't need to write a spice code for the simulation. If you're doing a transient analysis, you do a dot tran from 0 second to 1 second, and every single 0.001 second to plot 1 point. Okay? So if you look at the spice code over here, and let's see if this makes sense. I'm gonna specify this is a DC voltage, which is fine. You add a DC here. If you don't put a DC here, it's gonna treat it as a DC voltage directly. So VDD, what does this VDD mean? What does this mean? It's telling the spice this is the voltage. It could be VDD, it could be V anything, right? V Durango, whatever. And this VDD is a node name. It's naming that node as VDD. You can name the node as 1, 2, 3, 4 as numbers, or you can put a name on it. Doesn't matter. It's naming that node as VDD. It's the name of the node. Okay? And 0 is ground. So this voltage is dropping the voltage from VDD node to 0, and the voltage drop is 5 volts. It's a DC voltage. If you remove the DC, it's still treating this as the DC voltage by default. Okay? So this is another voltage. It's a V trip, just the name, but has to start with V. All right? And that's the name of the node, and that's the ground node, and it's 2.5 volts. Yeah, ground, you can name a ground, but you don't have to. You just directly give a 0, which is fine. But I think this one is not shorted to, you don't have a ground symbol here. That's why you have to specify it. And sine wave, spice called sine wave, V in, it's just the name. What is this V in? Node. What is this 0? Node. DC for sine wave? Seriously? What is it? Why do we need a DC voltage for sine wave? It's called what? DC what? Sine wave swing around 0. Sine wave swing around 2.5 volts. DC offset. Sometimes you need a DC offset. That's why you put a DC here. If you need the offset, put an offset. If you don't need the offset, put a 0. So it's gonna swing around 0. Okay. And sine wave, 2.5, 2.5, 2 megawatt, 2 megahertz. 2.5 and 2.5. What are these? It's one of them is amplitude, and one of them is the DC offset. It's really interesting. You don't put a DC offset here, but you put a DC offset over here, which also works, I think. So one of them is amplitude or magnitude. So what is the magnitude? This, right? It's not peak to peak. It's not peak to peak. Let's see. What about this? It's a pulse function. It's a pulse function. What's the first one again? One more time. I'm just repeating, right? So what's the first one? It's a name. What's the second one? It's a node. It's a node. Node as well. So it's a pulse wave. Pulse wave, the name of the pulse wave is V clock. And the node for dropping that voltage for the pulse is from clock to 0. And DC offset is 0. And here's the pulse function. Should I change myself to explain every single parameter for you guys? If I can remember it. What's the first one? I think it's 0. So it's from 0 volts to 5 volts as a pulse. Okay? 5 nanoseconds for time delay. So it's not starting that pulse immediately from time 0. It's a 5 nanosecond time delay. And 100 picoseconds for the rising edge. Don't worry about this. This is recorded. Okay? I know I'm going a little bit faster, but no worries. It's going to record it. What's the rising edge? This. 100 picoseconds. Should I make it very long or short? For digital signals, you don't want to make a very significant ramp here, right? It should be, ideally, it should be this, infinite. However, in real life, it won't happen. It does need a time delay, okay? It's a ramp. It takes time from 0 to 5. Okay, no matter how short that is, it takes time. So what's the time we define over here is 100 picoseconds. Rising time and falling time. Okay, 100 picoseconds for each. 4.9 nanoseconds for time on, so it's 4.9 nanoseconds, and the period is 10 nanoseconds. Are seeing it's not exactly 50% duty cycle. Does that matter? It's not 5 because this is 10. It's not 5. I think if you give a 5, it's gonna show some errors over here because you're having a little bit time loss for the rising and falling edge. So it won't be exactly 10 nanoseconds or double that on time. So give a little bit room for the computer to resolve. So usually give a 4.9 nanoseconds and give a 10 nanoseconds for the period, a little bit longer than that. So give the room for the rising and falling edges, okay? Just for simulation purposes. Clear on SPICE? It's recorded, so no worries. Can I move to the next step? Next topic? Okay, let's talk about the DAC. The DAC voltage calculation will be on quiz 2, which is on Friday. And on Wednesday will be a very simple circuits for, what was that? I think for Thevenins and SPICE. Be prepared for that, okay? On Wednesday. Oh, it's a Thevenins equivalent circuits and time delay. Oh, it's a very important topic to talk about. Now, why there are time delays? Oh, that's very important. So let's see, where should we start from? I got notes here. This one. They have learned this in circuit 1. Do you hate this type of problem? In circuit 1? Natural response, step response, close the switch at time 0. You're wondering, why do you have to close the switch? Play with the switch like a kid's. Okay? So you're asking for VCT, the voltage across the capacitor over time. Why is this important? In digital circuits, you have parasitic resistor and capacitor everywhere for every single transistor. That's why it's causing time delays. When you are doing integrated circuit design analysis, you are doing a clock tree to avoid all these time delays, to optimize the circuits. That's why you have to understand why you are getting time delays. All right. For example, this is a very simple model, and we are taking one of the cases to as example for digital circuits. So for this type of RC circuits, it has a resistor and capacitor. You are just using this as a model to model digital circuits because there are parasitic capacitors and resistors. So if you close the switch at time 0, this is a DC voltage. Sorry, should make it more clear. VC infinite. It's just basically DC voltage. Why? Because after you close the switch for a long time, you close the switch for 100 years. For 100 years, what's the voltage across the capacitor? No, after 100 years. I mean, I'm assuming the power plant will survive for 100 years. Yeah, it's gonna be 5 volts. Why? Because it's gonna be static, right? The 5 volts is always there. You close the switch, it's always there. It's applying the voltage across it. But only when you close it at the very moment, it's charging up the cap for a short period of time. But after that, it's going to be static 5 volts for forever. Okay, that's why I call it VC infinite. That is why. And you can see this kind of equation from all these different textbooks, but it's just showing the same concept. So what is VCT? If you didn't get it in circuit 1, and this is the place to master this concept, because it's super simple and it can appear on interview questions, all the interview questions. So VCT equals what? This is not a place to derive the equation for you guys. So I'm directly just writing this down, okay? Don't get frustrated. This is a place to master it. Looks complicated, actually super simple. But there are only 3 different cases. This is a general case, covers all different cases. It's basically you give a pulse, and eventually VCT equals this. I know this looks boring. Sometimes you see a long equation, you're gonna fall in sleep, right? So for case 1, initially, before I close the switch, the voltage across the capacitor is 0. So which means there's no voltage. It's exactly the same case. Oh, sorry, not zero. When it's not zero, when it's not zero. So there was some voltage stored in the capacitor at the very beginning. And then you close the switch. And you are trying to force it to a voltage of the source. So it's called forced response. Or step response, it's the same thing. So let me ask another question. Since I just told you guys, if I close the switch for 100 years, and the voltage here will become 5 volts, okay? So if I had a initial voltage stored in the cap, like 100 volts, okay? 100 volts in the cap, and I close the switch for 100 years, what the voltage of the cap will be after 100 years? 5 volts, why? Yeah, because the capacitor is going to discharge to the power source, right? But however, this power source is connected to the cord, the outlet on the wall, right? Eventually connect to the power plant, has infinite amount of charges, keeps charging, supplying that 5 volts to the cap. However, this guy has floating charges, only has finite amount of the charges stored in the cap, so it's gonna discharge. It has a higher voltage, right? Lower voltage, higher voltage, so it has a potential difference. It's gonna flow current in that direction because of the voltage drop. So eventually, it's gonna discharge this cap, and eventually it becomes 5 volts. It will be stabilized at 5 volts after 100 years. So VC was not zero. You are using exactly the same equation because you have to use all these parameters. VC infinite, which is 5 volts, plus VC zero, which is something stored in there at the very beginning, and minus VC infinite. So this is not something we are dealing with for this class. For digital circuits, it has a VC zero at the very beginning. So let's look at the second case. If VC is zero, what's going to happen? Just look at the same equation. VCT equals what? Important. You eventually find out, oh, digital circuits, oscillations, like all the clock signals and all these kind of things, it's basically just one special case of all the 3 different cases in a simple RC circuit. I'm going to write down the third case really quick. That's the second case. And the third case is VC infinite equals 0. So you are not using 5 volts to charge it up. So which means you don't have anything here. It's just a ground. And you close the switch at T0. Nothing is going to charge up the cap. So you have the initial charges stored at the cap. And what's happening here? It's just discharging. So this is called natural response. All right. So this simple example covers about 2 weeks of RC circuit classes in circuit 1. Summarized everything. That's everything you need to know. And a lot of times these kind of things appear on the interview questions. Could be one of the interview questions. So natural response, VCT equals what? It's simply just discharging from the cap, right? So what is VCT? It's just the initial voltage and discharge it using this attenuation factor here. Very simple, but this is not a case of our digital circuits. We only want to look at the second one, which is this one. Why? Because you close the switch, it's very similar to what? You got a clock and charging and discharging this cap. It's like a switch on and off. For this guy, you have a person switching this on and off. And for this digital chip, you just have to put a person inside the chip to switch it for you. Keep that guy busy. Okay. So VCT, for the second case, VCT equals VC infinite 1 minus this thing here. And VCT is what? 5 volts for most of the time, right? And can we just call it V in? Let's just simplify this circuit. It's basically a RC circuit to find out the time delay, okay? If you see this kind of question in the interview, you know how to deal with it. We'll get into the conclusion really quick. So it's V in what? It's basically just V in, right? V in. 1 minus this guy. Okay? So here's V out. What's going to happen is you got a digital circuit oscillating. Okay, the output will have a time delay. We'll do this. Okay. Why? Because it's delaying. You got this. And we are taking 50% of the voltage level, amplitude, and take the time out. And that's delta t, or we call it TD, time delay. And how do we calculate that? Since we have this equation. Anyone can tell me how do we calculate that? Gonna direct, it's gonna do a conclusion from this equation, super important. And you have to use it for one of the quizzes. Supposed to close notes on Friday, okay? Oh no, on Wednesday. Okay, what's the time delay here? Yes, RC something, right? It's not RC, but you can see this guy. I'm talking about 50%. So that's the definition for time delay. Keep in mind digital circuits. You just have to know this, okay? 50% voltage amplitude, and this is time delay. We can find out the answer from this equation. So 50% means so this is V out, right? So when V out reaches 50% of V in, we want to find out the T. So which means V out here becomes 50% of V in. Or V in is a square wave. I'm talking about the V in's amplitude. Okay, because V in is a pulse. Okay, V in is a pulse. So that V in is 5 volts pulse. Okay, something can be cancelled. And eventually this guy equals 0.5. And natural log on both sides. We're getting you can use a calculator to calculate it. This guy, right? I know it because I have done this for millions of times. So it's a negative 0.7 and cancelled. Are getting t equals what? That's delta t actually. Equals what? So that's a conclusion, right? Digital circuits. Doesn't matter what the voltage is. It could be 100 volts, could be 10 volts, doesn't matter. So the time delay for digital circuits, as long as it's for charging up the output, the time delay becomes 0.7 RC. Very important conclusion here. So what is the case of a failing digital circuit? The clock, you are trying to drive the circuit. You have a digital input, you are expecting a digital output, but eventually you are getting something like this. What's happening? Anyone can tell me what's happening? Do you have enough time to charge it up? For example, I give more time. Give more time. What's gonna happen? Same. Okay, reaches here. Since I have more time, so give the time to charge it up. Okay, then it works. So for this one, what's the problem? What's the problem in the circuit? The clock is too fast, and your circuit is too slow. Your circuit is too slow. You have a big R and big C. So the time constant is too big. It takes longer time to charge it up. For digital circuits, you need a digital output as well, right? So for this kind of thing, it's failing the circuit because your clock is too fast. Any question on this? No, not so far. No worries, since I'm gonna repeat this kind of things in the future as well. So after this class, definitely watch the video and lectures and go through all these equations and prepare for the quiz on Wednesday. So you do well on the quiz, you get confidence, right? So 30 points, I think. So if I'm telling you a circuit like this, let's see. Oh, he's looking at the question on the quiz. In R1, R2, and C. Are you able to find out the time delay for this circuit? You're comparing with this circuit. Oh, it looks different. I only have one R and one C in series. Okay, this guy got a one more resistor over here. So what should I do? Here the VL. Thevenin's, yes. Oh, here's VTH. VL is VTH. What is VTH? Voltage divider. I just showed you. Voltage divider. What's the voltage divider output? So VTH equals what? V in times what? R2 over R1 plus R2. It's a conclusion I just told you. That's VTH. What is RTH? Looking backwards. Because this is a, oh, one more concept. Even though it's a pulse, but usually we only looking at the DC voltage out as the voltage high, which is the DC voltage. That's why we don't consider this guy. We are assuming this is fully charged. So the cap is not in consideration. We are not looking at the complex impedance of the cap. Okay, digital circuits we are not. Keep in mind, it's only analog. Because you have to look at the time delay for the complex, right? The phase changes. For digital signal, no. If you are not fully charging up the capacitor, give more time. Never look at the time delays and phase changes. So for this one, ignore this guy and looking back, what's RTH? This is shorted, right? I know it's been a long time for circuit one, it's been like 2 years. Okay, so you're not familiar with this kind of concepts. No, don't worry about that. Go back and definitely review the Thevenin's and Ohm's law, all these kind of things real quick. Okay, what's the RTH? RTH is looking backwards and short this voltage source. Why? Because the ideal voltage source is like a wire. The internal impedance of the voltage source is 0. It's like a wire. And the internal resistance of the current source is what? Disconnect circuit, right? It's infinite. So the internal resistance of the voltage source is 0. That's why when we are looking backwards, we're gonna short it. So looking backwards, what's RTH? It's basically R1 in parallel with R2, right? Okay, so we can convert this part of the circuit to this. Ooh, this looks way better. That's V in over what? Oh, V in R2 over R1 plus R2, because that's VTH. That's C. Okay? Now what's the time delay? Easy, right? Yes, but we'll be on the quiz on Wednesday, okay? Whoever in this class will know what's going to be on the quiz on Wednesday, so that's the benefit of attending classes in the future. Keep in mind, 30 points, New Year gift. Got 7 more minutes. Let's see. Superposition. Superposition. Superposition is the most magical technique that I can use for circuit series in circuit design. A lot of times in circuit one, people don't cover too much about it, but actually it's one of the most important circuit series that I have ever used and learned. It's just beautiful. Let's see one simple circuit problem over here. I got R1, R2, V1, V2. What's the voltage here? Superposition, and this can be used for all these amplifier, operational amplifier design problems, all these adding circuits, summing circuits. And whenever you superimpose a DC offset to AC signals, you have to use superposition just everywhere. It's everywhere. You know, keep that in mind. Keep the superposition theory in your mind all the time. Very beneficial, useful. For here, and you're thinking about what? Mesh, node, what else? What else we learned? Mesh, node, superposition, whatever, okay? Let's just use superposition. V1 only. So when only V1 is applying or only functioning, short V2 to ground. Why? Because the voltage source is zero internal impedance resistance. That's why you short it. Whenever you're only looking at V1, you only look at the impact V1 give to the VL. So what is VL? Oh, that's a voltage divider. It's a voltage divider. I drew a ground symbol here. I didn't connect them, but actually they are connected. It's just one symbol is a ground, right? It's a common ground. So for this circuit, flowing a current in here, and it's a voltage divider. Just the one resistor, two resistors is a voltage divider. So VL equals V1 times R2 over R1 plus R2. And then you look at V2 only, V2 only. And this time you short V1 to ground. VL equals what? This time it's also a voltage divider. It's one single current flowing through the circuit. So we are getting V1 times R1 over R1 plus R2. So overall, VL equals these two VLs superimposed onto each other. So you are directly adding them together. That's why it's called superposition. So we look at V1 only and V2 only, and eventually we get two voltages at the same node, and we add them together eventually. So that will be the final VL. Yeah, me too.
And the equation for the V out, is it still V1 or when you're using V2 only?
Catch? Catch? Yeah, yeah. Whoa. So you guys are not falling asleep, which is great. Wonderful to teach a class with 15 or ish students. It's great. No one is falling behind. Hopefully for the entire semester, no one is falling behind. Every single one is getting 100% attention from me. Okay, so what are the office hours? It's a quiz question. If it doesn't work for you, since I know it's the same time for Monday, Wednesday, and Fridays, let's see. Where's my schedule? I think it's over here. The release calendar. Okay. If it doesn't work for you perfectly, definitely make appointments. Send me email. I will make myself available for you guys. For example, right after the class over here, right? So just let me know you want to meet with me, and I will sit in my office to, solve problem for you. And you can see it's one time ever for my teaching career. I have classes every single day in the week and in the early morning. So which means I have to work out every single day. I think that God just wanted me to run every morning in the week to keep me mentally healthy, um, which is great. So I can lose some weight. Um, but which is a good thing that after this class, I'll be free almost the whole day. I'll just sit in my office to help you guys with any problems. And I'll go to ski here. Uh, life is good, right? A lot of work. All right. Don't want to rush. Any other questions? Let me see if I cover every single thing for you guys to be ready for the quiz on Wednesday. Okay? Okay, it's exactly the same problem. Same problem. 7 is equivalent and do the time delay. Okay? Hopefully everyone can get 100. And for homework 1, you don't need to work on anything about homework 1. It's not available. Is it available now? It is. Okay, so it's a DAC calculation. So today we learned Staveling's superposition, and on Wednesday, we'll take most of the time to cover the way how do we derive the equations for this DAC, all right, and also some of the ADC resolutions, and that's it. And then you do the quiz, on Staveling's and time delay, all right. And on Friday you get another quiz on DAC. Make sense? Okay, cool. All right, that's it. Good to see you guys today.